This is FRM Part 1, Book 2, Foundations of Risk Management, and this is Chapter 2, Basic Statistics. Let's get right into the learning objectives. After completing this reading, you should be able to, are you ready for this? Tell everything about mean, standard deviation, skewness, and kurtosis. Those are the four moments of a distribution. So I want you to think about a distribution. And let's just suppose that we go back over the last 100 years of stock returns. And so think about a horizontal axis where we just identify all these points. And so let's truncate. Suppose there's no leverage. We truncated a minus 100% over here on the left, and then some big number over on the right, plus 100% or 200%. And so what tends to happen? What tends to happen is that the actual values of stock returns gets clumped, so to speak, in the middle. And there are extremes that occur in either tail. You know, for example, 1927, I think, was a big year. Maybe it was 28, 45% return. But then 1929 was a bad year, minus 45% rate of return. I think recently, 2013, we had a 40 or 45% return, but then in 2008 and 2009, we lost about that same amount. So we have all this stuff in the middle, and then as we move to the edges, as we move to the tails, we have fewer and fewer observations. And so that's a distribution. So the question then becomes, how do we measure this distribution? We need to figure out the clump. We need to figure out the dispersion, and then we need to figure out if it's tilted one way or another, and then we need to figure out what happens at either extreme. And so that's what we're going to do in these learning objectives. All right, so let's start with the clumping in the middle. Measures of central tendency. I love this definition, central tendency, because it tells us what happens in the middle. And what's important for probability theory is that what happens in the middle leads to a logical conclusion that sounds something like, these are the most likely outcomes. All right, there are three ways that we can do this. We can compute the mean, we can compute the median, and we can compute the mode. These are all measures of central tendency. And under certain types of distributions, we'll talk about that in just a minute, those things are all clumped somewhere near each other. But sometimes they're over here and sometimes they're over here. All right, let's do the mean first. I'm pretty sure you guys know how to compute the mean. I think we did this back in 3rd grade or 5th grade, some early grade. So what all we're going to do is we're going to sum all of the observations and then divide by the number of observations. Now it's important to distinguish between mu, which is the population mean, and x bar, which is the sample mean. So here, notice in the example I give you in the table, we have some scores on mock exams taken by FRM candidates. And so we have from 60 all the way to 72. Some of them occur more frequently than others. Some just occur once. And so we can compute the mean at 65. So remember, that's the first measure of this distribution of the clump in the middle. But we can also calculate the median, and the median is defined as that score that's right in the middle. So what we do is rank those things. So notice what I have in the bottom right of the slide. I have the 460s, then the 364s, and then, those higher numbers. And so note that 5 fall to the left and 5 fall to the right. There is an odd number, and so we can pick 64 as the median value. Now, if there were an even number of observations, we'd have to take the average of the two middle values. So back here, we've got 65 as the mean, then we've got 64 as the median, and then let's go ahead and compute the final one. This is the mode. This is the most commonly occurring value in the distribution. And so it's pretty obvious that we have 4 scores of 60, so that has to be the mode. Notice that distributions can be unimodal or bimodal or trimodal. I'm guessing that somewhere somebody has called a distribution quadmodal or quintmodal or octimodal, but I guess the term is multimodal when it's more than 3. All right, let's get back to this conversation about the difference between the population and the sample. A population refers to a summation of all the elements of interest to the researcher. So number of people in a country, number of hedge funds in the United States, or even the total number of FRM candidates in a given year. So think about the population as a summation of everything. There's nothing out here. It's everything inside of the variables that the researcher is trying to analyze. A sample is exactly what the name suggests. It's a sample of the population, and the sample is chosen so that it represents the population as a whole. I mean, look at my example. There are thousands and thousands of hedge funds in the United States. And so if you were a researcher trying to analyze hedge fund data, and you were to say, okay, I want to get the entire population, you'd have to go out and, according to one recent study, there's about 10,000 of these things out there. You'd have to go out and look at all 10,000 of these. How long would that take you? Way too long. So you pick a sample. You try to pick a sample of 30 or 60 or 100, whatever that number is, that's representative of the entire population, so that we can make reasonable conclusions about the sample, which then allows us to make reasonable conclusions about the entire population. All right, so what have we done so far? We've measured those clumps. So we're trying to figure out what happens around the middle. What is the average? Now what we want to do is we want to take a step back from our horizontal axis. We know what the middle looks like. Now we want to know how far can we go to the right and how far can we go to the left. In fact, standard deviation is sometimes referred to as the degree of error. How wrong are we with that central clump? Sometimes the central clump is right there and that explains lots and lots of stuff, but sometimes the central clump doesn't explain the whole story. So we can have a high standard deviation or a low standard deviation. Let me give you just a quick example. The standard deviation of a treasury security has to be 0 when we're talking about somebody who buys a treasury bill and holds it for, let's say, 90 days. If that investor holds it pays, let's say, $987 today, and then in 90 days gets the $1,000 back, well, because the market perceives treasury securities to be risk-free, well, then that standard deviation has to be 0. There's no doubt about what you're going to get at maturity. You're going to get that $1,000 back. Now, notice what we did back in the mean. The formula here is that we had the summation from I equals 1 to n of each observation. So we're going to add those, and then we're going to divide by n. Well, we're going to do almost the same thing to calculate the variance. What we're going to do is we're going to sum from I equals 1 to n, but now we're not summing just the individual observations. We're going to sum the observations and their difference between the mean. So now we're going to try to measure this thing called variability, maybe even volatility. And what we're going to do is we're going to take, notice inside of the parentheses, we have x sub I, so that's each individual observation, minus the mean observation. Now, the top formula is the population, so that's a mu. The bottom formula is the sample, so that's an x bar. And we're going to square that difference. And the reason that we square that difference is not to make life more complicated for researchers, but to make certain that we get rid of the negative, and the things that go this way don't exactly offset the things that go this way. Here's the example that I always give my students here. Picture me standing in front of the classroom, and I say, hey, let's play a game. Let's play a game called count the number of steps Jim takes. So I take 1, 2, 3, 4 steps, and I say, how many steps did I take? And everyone says 4, Jim. This is a stupid game. So then I go back to the starting point and I say, okay, this is what I want you to do. I want you to pretend like you're closing your eyes and closing your ears. Now count the number of steps that Jim takes. And so I go 1, 2, and then I turn around and I come back and I do 1, 2. And so I'm right back at where I started. And I say, okay, now pretend that you open your eyes and you open your ears. How many steps did Jim take? And they say, well, 0. But I still took 4 steps, but I ended up at the same place. So we square that difference so that we can count the true number of Jim's steps. Notice with the population, we're going to divide by n, just like we did back when computing the mean. But then when we're doing the sample, we're limited by these things called degrees of freedom. So we have to divide by n minus 1. So think of degrees of freedom in the following way. Let's suppose that I'm your professor and I gave you 2 exams. And the mean score on your 2 exams, which you know, is 15. And you know that you made a 10 on the first exam. The question is, what did you make on the second exam? Well, just some quick math will say that you had to know that you made a 20 on that second exam. The average of 10 and 20 is 15. So how many tests did you take? 2. If you know the mean, then you need to know one of those test scores to be able to back into the other test score. So that's kind of a simple definition of what degrees of freedom might look like. All right, let's go ahead and calculate the variance and the standard deviation. So when we square the number, we call it the variance, but we take the square root of the variance to get the standard deviation, because variance really has no logical or economic interpretation. When my wife asks me to go to the food store, she doesn't say, hey, Jim, get 12 squared pounds of potatoes. So very rarely do we deal in squared terms. So we want to get it back to its base level. So we have to take the square root. Should make perfect sense. So let's go back to that same data set. And on the left-hand column of the matrix in white over on the right, I've got the mean going down the right side. So that's 65. And we're taking each observation, 60, 60, 60, 60 minus the 65, then 64, et cetera, et cetera. So over in that middle column, I have the squared deviations from the mean. We sum those things and we get 270, divide by 10, we get a variance of 27, and take the square root and gets a standard deviation of 5.2. Right, so I want you to think about it this way. So the mean is 65, so that's the middle clump, right? And then the question is, all right, this is a score on the mock exam. So what can we reasonably expect to get on our next mock exam? And the answer is, well, 65. But then the question is, well, if we're expecting to get 65, how wrong can we be? And the answer is 5.2. We can be 5.2 wrong on our estimate of 65. That's why I always like to think of the standard deviation as the degree of error. Although that's not really a statistics term, but it helps explain that we're worried about stuff that happens to the right of the clump and stuff that happens to the left of the clump. All right, how about if we're doing this stuff with continuous random variables? And this goes back to what we talked about in chapter 1. All we're going to do is, when we're dealing with continuous random variables, is multiply the variable with its probability density function. So note, with the population, I've got the mu over on the left-hand side of the equal sign, and then I have the integral from the minimum and the maximum, right? You got to start somewhere and you have to end somewhere. And then there's that x, there's the continuous random variable, and there's its function. And for the median, we know that it's in the middle, so we just define that as 0.5, and that's what I have at the bottom there. How about expectations operators? So expected values are numerical summaries of these important characteristics. So we can take an expectation of the mean, and this is just going to be probability weighted. So notice what I have in that bullet point under expectations of the mean. The expected value is the weighted average of all possible outcomes of a random variable, where the weights are the probabilities, and that should make perfect sense. So the expectation for x, the expected value of x, is going to be the summation of the p. There's the probability of each outcome times each possible outcome. So however many possible outcomes we have, notice I go from 1 all the way out to n. So it's probably best just to show you a quick example here. So let's suppose that we have some possible returns, a probability distribution for a newly established hedge fund. So this is the way I like to think about it mathematically. So let's start on the left-hand side and say the following. We have a 20% chance of earning 8%. We have a 40% chance of earning 15%. We have a 30% chance of earning 20 and a 10% chance of earning 10%. If you look at it that way, it makes sense then that we're going to probability weight each of those returns to get an average. We're going to call it the expected return. So there I have the formula there at the bottom bullet point, 20% of 8 and 40% of 15 and so on. That gives us an expected return or an expected value of 16.6%. Now, one interpretation of that, and this is not completely statistically accurate, is that that 16.6% is the most likely outcome. But all we can say now is that it's a good measure of the clump somewhere in the middle, because notice that 16, it's to the left of some numbers and it's to the right of some other numbers. So here we have this distribution with only 4 possible outcomes. So extend this to, maybe hundreds or even thousands of outcomes. We can also take the expectations of the variance, and we're going to do the same thing, but instead of taking the expectations of all of the little x's, we're going to take the expectations of the difference between each observed x value and its expected value. Okay. Now, look at the middle bullet point there. Note that this can also be written as the expectations of x minus mu in parentheses squared, because the expectation of x is mu, is the population mean. And by expanding and doing some good math, we can get this very important result, that the variance is equal to the expectation of x squared minus the mean squared. And that's why we call this sometimes the root mean squared deviation. All right, so let's take a quick example here. Let's go back to our hedge fund. There's the distribution again. And let's go ahead and recompute the mean. There's that 16.6%. And then let's calculate the expected return squared. So what we're going to do is we're going to take that 20% probability times 8 squared, and then a 40% probability times 15 squared, and so on. And we get 312.8. To get the variance, of this distribution, all we need to do is take the difference between the 312 minus the 16.6 squared, right? We've got the expected r squared minus mu squared. And so that gives us 37.24. Take the square root of that and we get a standard deviation of 6.1%. All right, so what we've been doing so far is taking a look at the mean and standard deviation of one particular variable, like the rate of return on a hedge fund or the rate of return on an individual stock. And remember, those random variables could be almost anything. But this is what we know. When you put a bunch of stuff together, they don't operate in a vacuum. They interact, they interdepend, they depend on each other. So we need a measure. We need a measure of how they co-vary. In other words, when one particular hedge fund does something, does another hedge fund follow along? Is it kind of like play follow the leader? I mean, here are the choices. If you have one hedge fund who goes up by 10%, you have another hedge fund that could do, let's just say, one of 3 things. It could go up as well. Maybe it goes up by 12, maybe it goes up by 8. It could go in the opposite direction. Maybe it goes down by 12 or down by 10 or down by 8. Or it could do something totally independent of what the first hedge fund does. So we have those 3 possibilities. So we need a measure of that covariability. And this, of course, is extremely important in portfolio management, because this is what we know, that when investors decide on investing in portfolios, they're going to diversify their portfolios because everybody, even kindergartners, know that diversification reduces risk. And the reason that diversification reduces risk is because of the covariance between and among all of the stocks in the portfolio. So covariance is a great tool to decide how these two random variables behave with each other. So here's a good formula. Covariance between R sub I and R sub J. Those are just two assets. Let's suppose those are hedge fund returns. And let me quickly go back to that formula for the variance and standard deviation. So I want you to look at the sample down at the bottom. Note we have x1 minus x bar squared. I could rewrite that by saying x1 minus x bar times x1 minus x bar, right? So I want you to think about that. Think of it not with the 2 up there in the superscript, but think of it as 2xi's minus x bars. So what we're going to do here with covariance is that instead of xi minus x bar times xi minus x bar, we want the covariance. We want to substitute a different asset in there in the second part. So here we're doing returns, so we have an R instead of an X. So we're going to say the covariance between I and J is the expectations of R sub I minus the mean value of R sub I times R sub J minus the mean value of R sub J. So do you get it? Covariance is kind of like a general case of variance, but we're trying to measure covariability. So let's go ahead and compute covariance. So notice what we have here. We've got to have two different assets. So down the left-hand column, I've got two assets, A and B. So A returns 40, 20, and 0 in a strong and normal and weak economy, and B returns 20 and 15 and 4% in a strong and normal and weak economy. And then I've attached probabilities to those strong and normal and weak economies, 15 and 16 and 25. I'm sorry, 15 and 60 and 25%. And those, of course, sum to 100%. How can we compute the covariance between these two assets? So here's what we want to decide. Do these two assets move together? In other words, if there's a strong economy, do they move in tandem? If there's a weak economy, do they move in tandem, or do they move in opposite directions? That's really what we're trying to do with covariance. So covariance measures the strength and the direction of a relationship. All right, so here's what we're going to do. First thing we've got to do is calculate X bar. Let's calculate the mean. So notice in the first two circle points I have there, expected return on A, expected return on B. Those are just the probability weighted returns that we did in the previous example. Here we come up with 18% and 13%. All right, so now ready, let's do covariance. What we're going to do is, let's just do this first one here. We have a 15% chance of, right, this is a strong economy. With asset A, what is our degree of error? How wrong are we going to be if we think we're going to get 18? Well, we have a 15% chance of getting 40%, which is this far away from 18%. And then if we invest in B, we are going to get 20% in a strong economy, and that's this far away from the mean outcome. So you get the sense here that covariance, it's probability weighted again, but what we're interested in determining is how far away from the mean is each return. And we sum all that and we get 0.0066. And I'm glad we stopped there because I didn't want to put 00666 because that's the sign of bad things in an old horror movie. All right, so let's talk about covariance here. One quick last second before I move on to correlation. When you calculate covariance between and among random variables, you can get almost any number, like a minus 6,000 or 0.8423 or a plus 27.93. And so just like just like we don't go to the store to buy 12 squared pounds of potatoes, the covariance is kind of like, it's not a squared term, but it's a product. So it's kind of like a squared term. And as such, it can take on almost any value, but it's tough to interpret that value. So what good statisticians do all the time is they like to standardize a random variable. And so think about covariance can take on any of these values, but if we standardize it, look at the formula for correlation coefficient. We divide by the product of the two variances, the square root of the product of the two variances, or we divide by the product of the two standard deviations. What this does is it squeezes the covariance. It squeezes it all the way down to something that has economic meaning and that we can interpret it. Correlation coefficients, I bet you guys know this, always has to be either a -1 or a +1 or anything in between. So correlation measures exactly what covariance does. It's the measure of the strength and direction of a relationship, but it's standardized. So now we know that if the correlation coefficient between two assets is a +1, that means that whatever the first variable does, the second variable does the exact same thing. If the correlation coefficient is a -1, what that means is that whatever the first variable does, the second variable does the exact opposite. And then, of course, a correlation of 0 means that whatever the first one does, the second one does something that's totally independent. And so here's how I like to think about this, although this is not a great statistics interpretation, so do not tell any of your stats professors this. But think about this, that if we have a correlation coefficient that is 0.9, let's suppose it's the correlation between Walmart stock and Target stock. And so let's suppose that Walmart goes up by 10%. A correlation coefficient of 0.9 can loosely be interpreted that, oh, Target's going to go up by 90% of that 10%. So Walmart goes up by 10% and Target goes up by 90%. Goes up by 9%. So there's the 0.9. Now you can't say that from a statistical standpoint, but what you can get away with saying that over time, over many, many observations, that the correlation of 0.9 means that you get 90% of the covariability. I think it's helpful to understand correlation and covariance if you think of it in those kinds of terms. So the closer you get to 1 and -1, the stronger the relationship is. And that's the interpretation I have on those bottom 3 bullet points. All right, how about portfolio variance? This is going to be a really cool thing. So this is what we have. When we put assets together in a portfolio, let's just suppose there are 2 of them in this case, an A and a B. What we have to worry about is the variance of A, we have to worry about the variance of B, and then we have to worry about their covariance. All right, so a portfolio that's made up of A and B, the variance of this portfolio, look at the formula, it's going to be the variance of A and the variance of B. That should make perfect sense. Then plus, we're going to add the covariance term. So we're going to add 2 times the correlation coefficient between A and B times the standard deviation of A and the standard deviation of B. And that should make perfect sense because what we're doing, but the reason we have a 2 in there is because A covaries with B and B covaries with A. So we have to count it twice. It's not 2 because there are 2 stocks or 2 assets in this portfolio. So I want you to think about the variance of a portfolio or the standard deviation of a portfolio as having essentially 3 components. It's got the variability of A and the variability of B and then the covariability. All right, I guess it's time to do an example here. So let's suppose we have asset 1 and 2. We have 80% invested in asset 1, 20% invested in asset 2. Expected returns and standard deviations are given. So maybe we computed those like we did in the previous slides. So we have returns of about 10% and about 16%, right? Standard deviations of 17 and 30% and the covariance of 0.005. All right, so let's go ahead and do the 2 things that we've done so far. We've calculated the mean and the standard deviation. So the mean is going to be a weighted average, right? So we have 80% of our portfolio is providing us with 9.98, and then 20% of our portfolio is providing us with 15.8%, right? So we just take that weighted average. And so if we invest in asset 1 and asset 2, we can reasonably expect to get 11.14%. That's the expected return on the portfolio. But let's go ahead and compute the portfolio variance. What we need to do is we need to square those things. So the squared, we're raising it to the second power because in a portfolio context. Now let's go back to that simple formula. I don't want to scroll all the way back to the beginning in that formula for the variance, but remember we had xi minus x bar squared. Well, you have to do that stuff in order to get the portfolio variance. So there's a lot of squaring that goes on. And when you do the algebra and you do the summation and you cancel everything out, you get a lot of squared numbers. So we're going to take the weight squared, 0.8, times the standard deviation squared, which is the variance. So we got 0.8 squared times 17 squared, right? And so we're going to do this all the way through for asset 1 and asset 2. And then we need to do that covariability term. So 2 times 0.8 times 0.2 times the covariance. And so that gives us 0.023696. Take the square root of that, and we get a standard deviation of 15.39%. Now, it's at this point that you guys should be jumping up out of your seats saying, oh, this is what it means about diversification and risk reduction. Notice that what we have. We started with asset 1 that had a standard deviation of 17%, right? So it has this much variability, it has this much risk. We're adding a second asset that has 30% standard deviation. All right, so it's not quite 2 times, but let me just get away with saying it's almost twice. So we have this much variability. We're adding an asset that has almost twice that variability. So what are you just in your brains, what are you thinking? Oh, if I'm adding a riskier asset, one that has more variability, my variability ought to go up. That's kind of a logical thing, but no, that's not true. Because of the covariance between asset 1 and asset 2, standard deviation actually falls, right? Can I round that to 15%? So think about that. You start with 17, you go up to, you add one that has 30, and you reduce the portfolio standard deviation. So in financial analyst terminology, you have 17% risk, you add a 30% risk, and the risk goes down. This is the beauty of diversification, and it warrants you jumping up and running around your living room and high-fiving your husband or wife or your children and saying, yes, this makes perfect sense. All right, let's introduce this concept of moments. Remember when I gave that first example about the last 100 years worth of stock returns, I said something like, we want to know the clump, and then we want to know the dispersion, and then we want to know if it tilts to the left or right, or if the tails are up or down. Well, what we're going to do is try to measure those farther moments by giving them specific names. All right, so the first moment of the distribution is the mean. We did that. The second moment of the distribution is the variance or the standard deviation. But there are third and fourth moments. And this is how I want you to think about this. You guys know I like to give sports analogies, so bear with me for just a minute here. Let's suppose you're a golfer and you stink at putting and you decide to spend $400 on a new putter. So you go to the athlete store and you see all these putters there. And so you're going to look at all 4 moments of the putting distribution. I'm making these words up here as I go along. And so what's the mean? What you're going to do is you're going to look at the price tag and you're going to pick the putter up and you're going to see how it feels in your hands, and you're going to put it down and you're going to look at the feel of it. Okay. So you're going to say, okay, I like the mean. I like how it feels in my hand. I like how it looks behind the ball. Are you going to buy the putter based on that alone? Of course not. So what you do is you put a ball down. A lot of these places, they have practice putting greens. So you put a ball down, and there's a cup over there 6 feet away. So you take it back and you stroke it, all right? And so you stroke it and you stroke it. That's going to be the standard deviation, because what you want to do is how consistent are you when you go back and forward? I mean, if you're going like this and going like this, you probably don't want that putter. So we're going to go back and we're going to go forward. So that's measuring dispersion. So before you buy this putter, you go up to the owner of the store and you say, boy, I really want to buy this expensive putter, but I need to go out onto the golf course. Can I borrow it for a day? Let's just suppose the guy says sure. So you go out on the golf course on a beautiful sunny day and you play 18 holes. And so you're practicing your putting. And what you want to do is you want to know is, are you pulling it to the left or are you pushing it to the right? All right. If you're pushing it to the left, that's going to be the third moment. If you're pushing it to the right, that's going to be the opposite of the third moment. It's going to be part of that third moment. So let's suppose that you like what's happening and you think, all right, I need to figure this out in extreme conditions. So you go out and putt and you play around a golf when it's 4 degrees outside and it's snowing. And then the next day you go out and play around a golf when it's 110 degrees and it's boiling outside. So then you decide to buy the putter because you like the mean, you like the standard deviation, you like the skewness, and you like the kurtosis. All right, so thank you for indulging me there. So I think that kind of helps explain what's going on with these extra moments. Now, with a normal distribution, all we need are the first 2 moments. But there are distributions that are skewed and are characterized by kurtosis. So the third moment of the distribution is skewness. So look on the left graph that I have. Here's a symmetric normal distribution in which, and I said I would get back to this earlier, here we have a condition under which the mean and the median and the mode are identical. That's the definition of a normal distribution. But note that we can have positive skewness. We have more observations to the right, or we can have negative skewness. We have more observations to the left. Okay, so here's the definition there in my circle points. If the mean is greater than the mode, then skewness is positive. If the mean is less than the mode, it's skewness, and then if they're equal, then skewness is 0. How about kurtosis? So think about this distribution, this beautiful picture. Let me go back here. This beautiful picture on the left, which is the normal distribution. And so what kurtosis does is it measures the height of the tails. With a normal distribution, let me draw this here. You go like this and you go out there, and those tails, they never really kind of touch the horizontal axis, but they get really, really close to it. Well, kurtosis is, boy, are those things far away? So if they're scrunched together, then you're going to have a higher mean, and if they're spread out, you're going to have a lower mean. And so the formula for kurtosis is x minus mu and raised to the 4th power. So that's really what you're doing with the third and the fourth moments, raising it to the 3rd power, raising it to the 4th power. So notice the circle points I have here. The k that we describe here, the kurtosis, if you subtract 3 from it and you get greater than 0, this is called leptokurtotic. So you have like kind of the skinnier thing in the middle. If k minus 3 is less than 0, then it's kind of flatter. That's the platykurtic. And then k minus 3 equals 0, then that's the normal distribution. So the reason that we subtract 3 is that k is 3 for a normal distribution. Oh, wow. Now, just like we talked about covariance and correlation coefficient with the first and second moments of the distribution, we can ask ourselves the question, at the 3rd and 4th moment, is there a relationship between skewness and kurtosis? So we call this co-skewness and co-kurtosis. And so these things are used as part of an analysis of the overall distribution, but a lot of times they're used in asset management to try to determine which particular assets are more likely to outperform in the 3rd and the 4th moment. Like, for example, if we have, here, let me go back here real quick. If we have, let's take the middle example. If we have positive skewness and we have positive co-skewness, what that means is that if we're going to get some of those right tail distributions, which are good, right? They're good. And what we want to do is if one gets those positive co-skewnesses, then we want the rest of our portfolio to follow along, right? We want that 3rd moment to drag our portfolio to outperformance. Let me go back here. All right, so high kurtosis means that there's a high potential for extreme positive returns. Remember now, Coskewness is going to measure how far we're tilting, and Kurtosis and Kurtosis is going to measure what was happening in the tails. All right, the last part of those learning objectives deals with these point estimators, these best linear unbiased estimator. So think about what we're doing. We have this distribution, and then we have a sample, and so we have to pull something out of that, like the mean, right? The mean is going to be a point estimation from the sample. It's our best guess or best estimate of an unknown population parameter, and it could be standard deviation or any of the moments. And there in my circle points, I have sample mean as a point estimate of the population mean, sample variance is the point estimate of a population variance. What we need is we need a good point estimator. And so here is what the learning objective really tells us. So 4 desirable properties of an estimator. It's unbiased. It's efficient in the sense that we're trying to minimize the variance. It's consistent, meaning that you get it whether you do this or you do this or you increase the sample size. I mean, that's the technical definition of consistency. And then you can use it in a linear function. According to statisticians, the best estimator among all unbiased estimators is one whose variance is the minimum. And that should make perfect sense. And I think that takes us through chapter 2. So we did lots and lots of good stuff. We described, but we did a lot of calculations. So next up, we'll talk about distributions.